define and analyze vacuum tower with heat integration. In this video, you will construct, run, analyze, and manipulate a vacuum distillation tower. The vacuum distillation system is initially set up as a simple absorber model and is further detailed by adding bump-around side operations. You will also use the recycle operation for assistance in setting up heat integration between the atmospheric crude column and the preheat train you built in previous videos. This will serve to provide available heat duty from one section of your process to another, thus creating a truly integrated refining process simulation. Vacuum towers are commonly used in the refining industry for further process the bottom product of an atmospheric column. The vacuum tower distills the atmospheric bottom's product under reduced pressure, enabling further recovery of the petroleum distillates at a reasonable operating temperatures. Process streams at high temperature contain energy that can be recovered. Great examples of this bump-around streams associated with crude refining columns. Using these high-temperature process streams instead of hot process utilities is vital in helping to keep operating expenses to a minimum. This video will show you how to address heat integration studies within aspen hysys. This video includes the following tasks. Task 1. Add the vacuum tower. Task 2. Introduce site operations. Task 3. Export bump-around streams. Task 4. Material stream heat integration. Task 5. Energy stream heat integration. Task 1. Add the vacuum tower. Atmospheric distillation raw crude is typically temperature limited to temperature conditions below 360 degrees centigrade to 380 degrees centigrade. At higher temperatures, the crude could thermally crack and form equipment clogging petroleum coke. As a result, a significant amount of heavy hydrocarbon resid is produced from atmospheric column, which require further processing. Vacuum distillation towers operate at very low absolute pressures, thus enabling further fractionation of crude residues at temperatures less than 360 degrees to 380 degrees. Typical vacuum distillation units provide excellent vapor-liquid contact while also maintaining less pressure drops throughout the column. Bump-arounds are also typically present to help control liquid reflux. The products from vacuum distillation towers normally involve an off-gas, light and heavy vacuum gas oils, and a vacuum residue. Open aspen hysys and load the case saved at the end of the atmospheric crude column video. If you cannot find this file, load the attached file with this video. Before being fed into the vacuum tower, the atmospheric residue need to be configured at a vacuum pressure condition and heated slightly. Remember that most convenient means to fix stream conditions via a unit operation in aspen hysys is with either the heater or cooler operations. You will use a heater operation in this case. Add a heater operation to the flow sheet. Change the name to vacuum heater. Set the outlet stream to atmospheric residue. Name the energy stream. Name the outlet stream. Set the vacuum feed temperature to 395 degrees centigrade. And set the pressure to 15.2 kilopascal. Add a material stream to the flow sheet. Name the stream vacuum steam. Set the temperature to 150 degrees centigrade and set the pressure to 151 kilopascal. Set the mass flow to 1,800 kilogram per hour. Set the mole fraction of water to 1. Add an absorber column to your flow sheet. Open the column Input Expert. Change the column name to Vacuum Tower. Set the number of stage to 9. Select vacuum feed on the optional LED stages. Set the LED stage to 8. On the bottom stage inlet, set the vacuum steam stream. Name the overhead vapor outlet stream. Name the bottom liquid stream. Set the top stage reflex bump around. Keep the default bump around stage. Add optional side draws. The first stream is low heating value, gas oil. Set the type to liquid and change the draw stage to 2. And another stream, high heating value, gas oil. Set the draw stage to 6. Click Next. Set the top stage pressure to 11 kilopascal and the cooler delta P to 0 and the bottom stage pressure to 12.5 kilopascal. Click Next. Set the top stage temperature estimate to 120 degrees centigrade and the bottom stage temperature estimate to 370 degrees. And set the pump around rate to 275 cubic meter per hour. Click Done. Go to the monitor page and check any specification that do not have a specified value. To solve the vacuum tower, you will need to provide some specification. This procedure is the same as in any other column type. Simply click the Add Spec button in the design monitor page to add the new specs. Then activate enough specification until the degrees of freedom show as 0. Click Add Spec and choose column draw rate. Set the stream to vacuum overhead. Change the flow basis to mass. Enter a value of 2,300 kg per hour. Double-click on the light vacuum gas oil rate. Change the flow basis to standard ideal volume. Enter a value 32 cubic meter per hour. Do the same for the heavy vacuum gas oil rate and enter a value of 72 cubic meter per hour. Enable both light vacuum gas oil rate, and heavy vacuum gas oil rate. Now the column has conversion. This concludes the first task in this review. Task 2. Introduce site operations. At this point, the vacuum tower is set up in a very basic manner. The only heat into or out of the system is via the stream feed and the top stage bump around unit. You will modify the column by adding 2 additional bump arounds that will remove further energy from the column, lessening the load on the top stage bump around. Note that after making substantial changes to a column model, it may be necessary to click the reset button before clicking the run button to resolve. Reopen the property view of the vacuum tower. Select the side ops tab. Open the bump arounds form. Add another bump around. Name it bump around 2. Set the return stage to 5 and the draw stage to 6. Click install. Double click the first active spec. Change the flow basis to standard ideal volume. Set the value to 250 cubic meter per hour. Double-click the second active spec. Change the type to DT. Set the value to minus 30 million BTU per hour. Add another pump around. Name it bump around 3. Set the return state to 8 and the draw stage to 9. Click install. Double click the first active spec. Change the flow basis to standard ideal volume. Set the value to 310 cubic meter per hour. Double-click the second active spec. Change the type to GT. Set a value of minus 2,275,000 BTU per hour. Turn to the Design tab, the Monitor page. Check that degrees of freedom is equal to 0. Click the Run button to convert the column. The vacuum tower has solved at this point. However, it's preferred to replace the vacuum overhead draw rate specification as discussed in the atmospheric load column video. Using flow rate specification can make certain column models rather inflexible. Here you will replace the overhead draw rate with the top stage temperature specification. Deactivate the overhead rate specification. Click Add Spec. Select column temperature. Select the first stage. Set a value 120 degrees centigrade. The column has reconverted. This concludes the second task. Task 3. Export bump around streams. When you constructed the preheat train of your refinery model, remember how the heat exchanger unit operation was built. The raw crude was heated by an assumed heat bump around material stream. This hot bump around was set up with the same molar composition as the raw crude, just with a different flow rate, temperature, and the pressure. While this is a convenient approach, it doesn't truly represent the bump around fluid and associated heat transfer very accurately. In aspen hysys, it's possible to take the material flows associated with the column bump arounds and export them out for use in the main flow sheet. With this approach, you could replace the estimated hot bump around and cold bump around material stream in the preheat train with actual bump around flows from the atmospheric or vacuum column. This portion of the video will help you prepare the kerosene bump around streams for integration with the preheat train heat exchanger. Open the property view of the atmospheric column. Open the side ops tab. Select the bump arounds page. Check the export checkbox of the kerosene bump around. The column has reconverted. Return to the main flow sheet and check that kerosene bump around draw and kerosene bump around return have appeared. It's important to remember that these streams are calculated by the atmospheric column and its internal calculations. Therefore, if we try to attach them to the heat exchanger in the preheat train, the simulation would be overspecified. The heat exchanger is already solved with a defined minimum approach temperature specification. So to use the kerosene bump around stream's temperature difference as the heat transfer driving force, we must deactivate the minimum approach temperature specification on the heat exchanger. Open the property view of the heat exchanger. On the Design tab and the parameters page, read the shell side pressure drop, but keep the tube side pressure drop. The shell side pressure drop will be re-established by the known pressures of the kerosene bump around streams. Go to the specs page. Deactivate the temperature approach specification. Return to the main flow sheet and delete the hot bump around and cold bump around streams. Reopen the heat exchanger. Go to the connection page. On the shell side element, select kerosene bump around draw. And on the shell side outlet, select kerosene bump around return. You can see that the heat exchanger remains unsolved and no calculations are performed from the heat exchanger on downstream. This is because the feed to the atmospheric crude column is not defined and therefore cannot solve. If the atmospheric column cannot solve, the kerosene bump arounds are unknown, and if those are unknown, the heat exchanger can't solve. We need to find a way to initialize the atmospheric column model such that it can compute a kerosene bump around draw stream to go back solve the heat exchanger. The flow sheet will then need to resolve with the new heat exchanger output. This scheme will introduce an iterative calculation, which can be facilitated by adding a recycle logical operation. This concludes task 3. Task 4. Material stream heat integration. To facilitate heat integration between the heat exchanger and the atmospheric column, you will add a recycle operation just upstream the atmospheric column. The recycle outlet stream will consist of an initial estimate, thus allowing hysys to start calculations at the column. Once the column solved and the kerosene bump around draw is computed, it can go back and calculate the heat exchanger. New process conditions will push their way towards the atmospheric column as the preheat train portion of the simulation solved. These new conditions arrive at the recycle and serve to update the initial estimate you provided. From there, the flowsheet will iteratively recalculate until material stream and energy balances are achieved across the recycle. Rig the connection between the atmospheric heat feed stream and the atmospheric column. Add a recycle operation. Set the outlet to atmospheric feed. Name the outlet atmospheric feed 2. Now connect the atmospheric feed 2 material stream to the atmospheric column. Defining its outlet stage as 28. As the atmospheric feed 2 material stream is an outlet to the atmospheric column, it must be fully specified. Open the atmospheric feed 2 stream. Click Define from Stream. Select Truck Road Stream. Choose to copy only composition and the flow. Then click OK. Enter a temperature of 400 degrees centigrade and enter a pressure of 248 kilopascal. Now the atmospheric feed 2 is fully defined. Open the property view of the atmospheric column and click Run. The column has converged. This concludes the fourth task of this video. Task 5. Energy Stream Heat Integration. Heat integration in Aspen hysys can also be attained using energy streams rather than material streams. The benefit to using energy streams is that the flowsheet typically will not require iterative calculation to solve. Therefore, no recycles and no initial estimates are required. These situations are typically much easier for the hysys user to configure. Use the atmospheric gas oil pump around from the atmospheric column to heat the rock wood at the entrance of the preheat tray to recover as much heat as possible. Since it is a heater model at this location and not a two-site heat exchanger, you only need to externalize the atmospheric gas oil pump around Q cooler energy stream. Go to the design monitor page of the atmospheric column. Deactivate the atmospheric gas oil pump around duty specification. The column status is changed to unconverged. Go to the Design Connections page. Click the stream cell beside the atmospheric gas oil pump around Q cooler. Select H1Q. As you can see, the flow sheet has reconverged using the energy stream of the atmospheric gas oil pump around. This concludes the last task in this video. Thank you for watching.